Another tool you should be aware of when working with the flat pattern of a sheet metal part is the corner trim feature, which allows you to add relief and break any sharp edges. Corner trim can be launched from the sheet metal toolbar or from the Insert Sheet Metal drop-down menu. Right now the command is grayed out. The reason this is that this new feature will be dependent on the flat pattern feature, meaning it will only be active in the flattened state. I'll go ahead and flatten the part. As soon as I do, the corner trim feature becomes available. I'll click on it, and the corner trim property manager will appear. To get started, I can click on each edge that I wish to add relief to, or I can use the Collect All Corners button to have Solidworks select all of them for me. Using the relief pull-down, I can set it to use square or bend waste, or I can leave it as circular. Whatever option I decide, I will also be able to adjust the size using this area, or by using the ratio to thickness option. When using the circular or square type, I can use the Centered on Bend Lines option to have Solidworks center the relief cuts relative to the bend lines. If I use the square type with the Centered on Bend Lines option, I also have the Tangent to Bend option, which automatically sizes the cut so that it's tangent to the bend lines. I can add fillets to the corners of the reliefs by checking this option and adjusting the radius. The other section in the Property Manager I can adjust is the Break Corner options. This option allows you to remove material from external edges and add material to internal edges. To break all of the sharp edges, I'll click on the face of the sheet metal, and SolidWorks breaks every sharp edge that's touching the face. Notice the break option does not override the edges that were added in the relief options section. If I wanted to break one of these edges instead of adding relief, I must remove it from the relief options section by right-clicking on it in the Property Manager and choosing Delete, or by clicking on it again in the graphics window. You can see by the preview that SolidWorks is adding a chamfered break to the edges. I can adjust the size of the chamfer, or change this to filleted and adjust the radius. At this point, I'll go ahead and click OK to finish the corner trim feature. It's important to note that all of the settings we specified in this corner trim feature are for the flattened state of the part only. They do not affect the part in its folded state. To make changes to the corner trim feature, make sure the part is in its flattened state, otherwise the corner trim feature will be suppressed. You may have noticed the base flange button we use to insert our base flange is actually called Base Flange Tab. All this is because this button has two uses. It will create a base flange to begin a sheet metal part, but once you have a sheet metal part started, the same button can be used to create a tab. The tab feature is used to add material with the same thickness and direction as an existing sheet metal face. To create a tab, simply begin a sketch on an existing sheet metal face and create a profile. The profile can be any shape as long as it overlaps the existing material. With the profile completed, I'll exit the sketch and click the tab icon. If you don't have a sketch pre-selected, SolidWorks will ask you to choose a sketch for the tab. The properties here are the same as we saw earlier when we created the base flange, so I'll simply click the green check, and the tab is complete. If you need to make any changes later on, you can click the tab feature in the Feature Manager tree and either edit the sketch to change the shape of the tab or edit the feature to change its properties. In addition to adding flanges using the edge flange and miter flange features we've already seen, you can also create flanges by bending flat pieces of sheet metal. You can do this using the Sketched Bend feature. Let's take a look at an example. Here we have a flat base flange. You might recall that when the base flange feature is used, the part is defined as a sheet metal part, making other sheet metal features available. One of those features is the Sketched Bend. When you click the Sketched Bend icon on the sheet metal toolbar, SolidWorks prompts you to select a face to sketch on. I'll select this face. The sketch used for this feature requires a line that will define the location of a bend. I'll sketch a line that goes from one side of this inner tab to the other. The line does not have to cross the entire tab to bend it. I can sketch the line smaller than the tab if I wish. However, if you attach the line segment to each side of the tab, you can prevent errors that might come up in the future if you make changes to the shape and size of the tab. Another reason to attach the line segment is to prevent the line from extending into the surrounding material. If the line is long enough to extend into the surrounding material, it will be affected by the bend as well. Once the sketch is complete, I will exit the sketch to bring up the Sketched Bend Property Manager. The first item is a selection box prompting you to select a fixed face. When using the Sketched Bend feature, one side of the sketch line will remain unchanged while the other side is bent. By clicking a face, you will define the side that will remain stationary. I'll click on this side of the line, and you can see the selection box is filled. Next is the option to choose where the bend is located in relation to the sketch line. You can choose between center line, material inside, material outside, or the entire bend outside. These options will be available with most sheet metal features that create new bends, such as the edge flange and miter flange that we've already seen. Bends created using the Sketched Bend feature can be any angle from 0 to 360 degrees. You enter the angle here, and you can use the reverse direction button if you need to change the bend to the opposite side. These last options we've also seen in previous features. They allow you to change the default bend radius and bend allowance. I'll use the defaults in this case. Once you click OK, SolidWorks adds the bend. Sometimes referred to as an offset or joggle, the jog command is used to add a jog to a flange like you see here. To add a jog to a flange, you must define where the bends for the jog will be located. You do this by creating a sketch. I'll click the jog icon on the sheet metal toolbar, and because this is a feature that requires a sketch, SolidWorks prompts me to select a planar face to sketch on. I'll select this face, and a new sketch is created. This sketch only requires a line to tell SolidWorks where the bend should be located. The line does not have to cross the entire flange, but it's a good idea to attach it to the edges in case you make a change to the flange in the future. To further specify the location of the bend, I'll add a dimension. When the sketch is complete, I'll exit the sketch, and the jog property manager appears. Notice that when a jog is added, I can either keep this face fixed and bend this side up, or the other way around. To specify which face should remain fixed, I'll just click on this side of the sketch line, and you can see the face appears in the fixed face field of the property manager. I can also click the reverse direction button to change the direction of the jog, or click the arrow in the graphics area. Like most sheet metal features, I have options to define a bend radius and bend allowance that are different from the default settings for this part. I'll keep the defaults in this case. The jog offset distance can be defined as a blind distance or any of the other conditions listed here, such as up to vertex, up to surface, or offset from surface. Depending on the condition you select, you can choose how the offset distance is measured using these buttons here. The Fix Projected Length option is important when using the jog feature. It controls whether more material will be added to create the jog, or if you're simply going to bend the existing material. Note the change in the preview as I check and uncheck this option. With the option unchecked, the tab's overall length is shorter once the jog is added. With the option checked, more material is added by SolidWorks, so the overall length of the tab is the same after the jog. The next section controls the position of the bend in relation to the sketch line used to make the jog. The available options are to use the sketch line as a center line for the bend, to keep the material inside or outside of the sketched line, or to keep the entire bend outside the sketched line. In this example, I will use the first option, which is bend center line. The last thing to specify is the jog angle. This is where you can change it from the default of 90 degrees to an angle of your choice. The hem tool, as the name would indicate, is used to fold over an edge of a sheet metal part. Let's take a look at some of the options available with this feature. To add a hem, I click on the hem button from the sheet metal toolbar. The first thing I need to do is select the edge I wish to fold over. These two buttons control whether the bend is added to the inside or outside of the existing edge. You can also click the reverse direction button to fold the hem to the opposite side. If you don't want the hem to extend the entire length of the edge, you can click on the Edit Hem Width button. When I do, a message window appears telling me if the sketch is valid. I can edit the sketch line to control the length of the hem, and I can also add dimensions or relations to further define the sketch. When finished editing the sketch, I can click either the Back or Finish button. The Back button will save the changes and return to the Property Manager, while the Finish button will complete the hem feature. I'll click the Back button. The next section is where you can adjust the type and size of your hem. First, you must choose from the 4 different shape options. Notice as I click on each of the 4 types, the parameters underneath the button change to reflect my selection. In this example, I will choose the teardrop shape and specify an angle and radius. I click OK, and the hem is complete. It is possible to create a hem on more than one edge. Hems can be added to multiple sides of a sheet metal part and even non-linear edges, all in the same hem feature. If you choose a combination of linear and non-linear edges, one thing you must keep in mind is that the non-linear edge must be tangent to the linear edge for it to work in the same feature. Notice the hems are trimmed appropriately at each corner, similar to the way a miter flange behaves. The closed corner feature allows you to control the appearance of sheet metal seams. In this part, I have a corner where 2 flanges of a miter flange feature meet. The closed corner feature will allow me to extend one of these flanges to close this gap. To close the corners, I click on the closed corner icon on the sheet metal toolbar. As you can see, there are not many options to this command. All I have to do is select one of the 2 faces creating the gap and choose the type of corner I wish to create. In the Property Manager, notice there are 2 selection windows, Faces to Extend and Faces to Match. These 2 selection windows will be used to choose the opposing faces that will be extended to close the corner. Typically, the first step is to specify the corner I'd like to close in the Faces to Extend selection box. After a face to extend is selected, you then tell SolidWorks which other faces meet at the corner in the Faces to Match selection box. Before I select anything, notice the Auto Propagation and Coplanar Faces checkboxes at the bottom. These will be enabled by default. With Auto Propagation enabled, when I select one of the corner faces, it is added to the Faces to Extend selection box. SolidWorks will attempt to automatically make the appropriate selection for the Faces to Match selection window like you see here. Because I have the coplanar faces checkbox selected, SolidWorks looks to automatically add any faces that lie in the same plane to this corner. But in this particular example, there are no coplanar faces, so the option has no effect. If I clear the selections, the auto propagation checkbox clears, and I need to either make the selections manually or recheck the box. The three available corner types are butt, overlap, or underlap. The butt type will extend both flanges, leaving the smallest possible gap between them. The overlap and underlap types will extend one flange to close the corner. You'll notice that although the corner is being closed, the two flanges are not being fused together. Rather, the gap between them is being minimized. You can control how much of a gap to leave by changing the gap value in the Property Manager. Also, when using the overlap or underlap option, you can specify a ratio that will determine the extent of the overlap. This ratio can be any value between 0 and 1. When using 0, there will be no overlap. When using 1, you will have a full overlap. I'll click OK, and the closed corner feature is complete. By the way, I could have selected more than one corner to close. If you do select more than one corner, the same corner type you select will be applied to all corners. I will show you one more example using a more complicated corner. This part has an extruded cut that cuts into the corner. I'll activate the closed corner feature and select the faces along one side of the corner. I'll activate the Faces to Match selection window. And to make sure the corner can be made, select the corresponding faces in the same order as before. I'll make sure the corner type is set to butt, then click the green check to finish closing the corner. The break corner feature is used to fillet or chamfer sharp corners of a sheet metal part. To activate the feature, click on the break corner icon on the sheet metal toolbar. In the Property Manager, I'm prompted to select the corners I wish to break. As I move the pointer over the part, notice only two types of entities are highlighting. The break corner feature activates a filter that will only let me select the small edges of external corners or faces. If I select a face, any external corners will be selected. In addition, if I window select the entire part or a portion of the part, only corners will be selected. In addition to selecting corners, you have the option of selecting either chamfers or fillets in the Property Manager. Depending on which option you select, you will enter a fillet radius or chamfer dimension to use. I'll click OK, and you can see the sharp corners are gone. If you're wondering why you wouldn't use a regular chamfer or fillet instead of the break corner feature, it's really just a matter of convenience. The break corner feature makes it easy to select external corners by using a filter, as you saw earlier. You can use the fold and unfold features to temporarily flatten bends in your sheet metal parts, allowing you to create features while the part is flattened. For instance, an extruded cut across the bend region. To temporarily flatten a bend in a sheet metal model, you can use the unfold feature. Using the unfold feature is easy. I'll launch it from the sheet metal toolbar. This is the Unfold Property Manager. You can see there are really only two fields I must specify: a fixed face and bends to unfold. The unfold feature is pretty intuitive. Imagine you were to clamp this part and unfold the bends using a pair of pliers. That's basically what the unfold feature will be doing. The fixed face would be the face that you clamp, so I'll choose the bottom flat face of the part. For the bends to unfold, I can either use the Collect All Bends button to unfold every bend in the part relative to the fixed face, or I can choose the bends manually by selecting them in the graphics area. Instead of using the Collect All Bends button, I'll only unfold this single bend here. So I'll select it, and when I click the green check, you can see it's unfolded. Now I can create additional features with the bend unfolded. I'll show you why this is useful in a later lesson, but for now, to return the part back to its bent state, I can use the Fold feature to refold the bend. The Fold feature Property Manager looks identical to the Unfold feature. I'll select the fixed face, again select the bend, and click the green check. The bend is folded back up. Notice the feature is added to the tree. And just like any other feature, it's a time-dependent feature, meaning I can use the rollback bar to go back to before the feature is added, suppress and unsuppress the feature, and edit it just like any other. When it is necessary to remove some material from a sheet metal part, you must use an extruded cut. For the most part, the extruded cut works the same in sheet metal parts as it does in a regular solid. You start a sketch, create a profile, a simple circle in this case, and then extrude the cut. Notice the Extruded Cut button appears on the sheet metal toolbar. This is the same button on the Features toolbar, it's just provided here for convenience. There are two settings that are different in the Extruded Cut Property Manager when you're working with a sheet metal part: Link to Thickness and Normal Cut. Link to Thickness allows you to create a cut that will be the same depth as the thickness defined for the entire sheet metal part. This is helpful for two reasons. If you later decide to increase the thickness of your part, any cuts using the Link to Thickness option will still go through the sheet metal. The second reason is that if you use the Through All end condition, there might be material on the other side of the part that will be cut unintentionally. Let's take a look at another part to examine the normal cut option. In this example, I'll create a cut on this face. I'll make the end condition through all, so both the vertical and angled faces will be cut. First, let me clear the normal cut option and click OK to complete the cut. The problem here is with the cut on the angled face. Notice the cut comes in at an angle. When sheet metal is manufactured, cuts are generally made directly into the flat pattern, then folded. If I edit the cut feature and enable the normal cut option, the cut on the angled face will change to reflect the way the part will actually be manufactured. If you've ever found yourself manually sketching lines to represent a cross break on a sheet metal part, Solidworks has a tool that will take care of that for you. Here I have a simple sheet metal part, and I want to add a cross break from the bottom face to give it some more rigidity. I can activate the cross break tool from the sheet metal toolbar or from the Insert Sheet Metal drop-down menu. The selection box asks me to select the face or faces I would like to add the cross break. I'll select the bottom face. I can use the reverse direction button or click the arrow in the graphics area to change the direction of the cross break. You can also use the Edit Cross Profile button to edit the position of the sketch lines. When I click it, a window appears saying that the sketch is valid. Notice the sketch lines have coincident relations at each corner. If I delete one of the relations and move the sketch inward a little bit, the message window tells me that one of the endpoints of the sketch is not on one of the face's edges. As soon as I create a coincident relation between the endpoint and the edge, the message window tells me the sketch is now valid. I can make more changes to the sketch as long as each endpoint is on an edge. Once I'm finished making changes, I'll click back to return to the Property Manager. The next two options let me define the break radius and the break angle of the cross break. Keep in mind that the cross break feature does not actually change or deform the model in 3D. The idea behind this feature is that it will automatically create the sketch lines, reference dimensions, and annotations that appear in the drawing to represent a cross break. When I click OK, the cross break is created. Notice that nothing has changed other than the appearance of the cross break lines. This is simply a representation of the cross break. I can still add edge flanges to the other edges of the part, and I can flatten and fold the part without any problems. At this point, I'll create a drawing to show you how the cross break is represented in a 2D drawing. When I insert the flattened view of the part, you can see the annotation that is given to the cross break. It shows the direction of the cross break, the bend angle, and the bend radius that I specified in the Property Manager. The Sheet Metal Gusset feature allows you to quickly create gussets to reinforce your sheet metal parts in situations where a bend exists, like in this example. Let's create a gusset to strengthen this bent sheet metal part. I can open the Sheet Metal Gusset Property Manager by clicking its icon from the Sheet Metal toolbar, or I could go to the Insert drop-down menu, Sheet Metal, and select Sheet Metal Gusset. In the Position group box, I'll make selections to determine the location of the Sheet Metal Gusset feature. In the first selection box, I'll select the two planar faces adjacent to the bend. Solidworks predicts the entities to select for the next two selection boxes and generates a preview. Usually the predicted selections work out well, but I'll go over what these two other selection boxes mean in case you'd like to make adjustments. The second selection box asks for a linear edge that the gusset will reference for its alignment, shown by this edge here in purple. The third selection box asks for a reference point, vertex, or linear edge from which an offset can be dimensioned, which right now is this vertex here. With the offset checkbox enabled, I'll enter an offset of 20 millimeters. In the Profile group box, I can set an indent depth to specify the size of a symmetric gusset, or I can create an asymmetric gusset by activating the Profile Dimensions option. Here I can specify the depth of each gusset leg, or I can specify an angle for a single gusset leg. I'll choose to create a symmetric gusset by selecting the Indent Depth option, and I'll use 20 millimeters for the depth. The icons at the bottom of the Profile group box let you choose whether to use a rounded or a flat gusset type. The flat gusset type option also gives you an additional option to fill at the edges. I'll choose the rounded gusset. Before I finish this feature, let's quickly go over options within the Dimensions group box. These allow you to further customize the shape of the gusset. The Indent Width option specifies the total width of the gusset, and the Indent Thickness option sets the thickness of the gusset wall. I'll set the width to 4 millimeters and the thickness to 0.8 of a millimeter. I can also add a draft by toggling the Side Face Draft icon and specifying a draft angle. In the same manner, I can also add inner corner and outer corner fillets. However, notice that since the acceptable range of corner fillet radii for this gusset is so small, the preview does not update to show the fillet. I'll leave these options turned off for now. Click the green check, and the sheet metal gusset is created. Notice, however, if I flatten the part, there is no indication of where the gusset will be created. If you want to include gussets in the flat pattern of a part, you'll need to go to Options, Document Properties, Sheet Metal. Under Flat Pattern Options, you can choose to show the gusset profiles or show the gusset centers. I'll enable both options, click OK, and you can see that the profile and the center of the gusset are now shown. Any gussets I create in this document will now automatically be shown in the flat pattern unless I override the document settings in the gusset feature. To do this, I'll edit the gusset feature. And in the Flat Pattern Visibility group box, I can enable Override Document Settings. Now I can choose which aspects of the gusset to show in the flat pattern, independently of the options set in the sheet metal document properties. In some situations, you may want to add gussets to adjacent surfaces that are not connected by a bend. In these cases, a sheet metal gusset can't be added, but you can create a gusset using a weldment feature instead. You can add gussets by going to the Insert, Weldments drop-down menu, and clicking Gusset. In the Property Manager, select the adjacent planar faces you'd like to create a gusset between. Specify the profile and location. If you frequently work with sheet metal parts in SolidWorks, you're probably already familiar with the various ways you can control how corners are created on the model. For example, by using auto relief, closed corners, or corner trims. The Corner Relief tool lets you quickly apply different types of corner treatments to a sheet metal part. The Corner Relief tool is similar to the auto relief options available from within sheet metal feature property managers. Both can be used when a relief cut is needed for a bend. The main difference is that the Corner Relief tool makes it easier to select and edit any or every corner of the part without having to configure the individual feature property managers. The Corner Relief tool also has a larger selection of corner treatments and an automatic corner selection capability. I'll show you how the Corner Relief tool works by adding relief cuts to this base flange at each of the bend corners. I can find the Corner Relief tool by expanding the Corners flyout menu on the sheet metal toolbar and selecting Corner Relief. Or I can open the Insert drop-down menu, and under Sheet Metal, I'll click Corner Relief. Before going through any of the options, I'll switch to a top view of the metal sheet. The Scope selection box lets you specify the sheet metal body for the corner treatment if you're working with a multi-body sheet metal part. This part file contains only a single sheet metal body, so it's been pre-selected. You can select the individual corners where you'd like the relief cuts to be added in the corner selection box, or you can click the Collect All Corners button so that every corner between the bends is automatically selected. Notice that the Define Corner selection box automatically populates with the faces that correspond to the selected corners. The Define Corner option can also be used to specify corners if they have not yet been selected by the Corners selection box. To do this, you would select the faces that define the corner and click the New Corner button. But in this case, the Collect All Corners option selected all of the corners I need, so I can leave this alone. Under the Relief options, you choose the type of relief and preview it by selecting the corresponding icon. I'll zoom into a corner so you can see the preview a little better. The available relief types are rectangular, circular, tier, obround, and constant width. Notice as I click through each relief type, each one has a set of options specific to its type. I'll select circular, and you can see the parameters update. I'll set the slot width to 0.8 of a millimeter, and leave the other settings at their defaults. When I click OK, the feature is completed. Corner relief features also carry over to the flat pattern. Notice when I flatten the part, you can see the relief is still there. Corner relief features are also configurable. I'll suppress the corner relief that I just made. Next, I'll create a new corner relief feature that uses a constant width relief type. Then I'll go to the Configurations Manager and create a new configuration. I'll activate the default configuration, and from the Feature Manager design tree, I'll suppress the new corner relief and unsuppress the previous corner relief. Now, if I head back to the Configurations Manager, I can switch between the configurations to see each type of corner relief.